All right, welcome. We are going to do 3-1, which is solving systems of equations. There's many different ways to solve systems. We're going to do it by graphing today. Your book will talk about using tables a little bit, but we're actually not going to cover that part. We'll just be solving by graphing today, and then we'll use algebra rules a little bit later. So what is a system of equations? It's going to be two or more equations that relates two or more unknown variables. Those can represent real life situations, but what's important is those variables represent the same types of things. And the solution of a system is what makes both equations true. So we can solve those using algebra, which we're going to talk about a little bit later in chapter 3, or by graphing. And when we talk about graphing, your solution is going to appear where the lines cross. That represents the x and the y value that both lines share. Okay, so our steps. We want to graph both lines. Use the method of your choice. Some of you love slope-intercept form. I think that's the easiest. Some of you don't mind doing it by the intercepts. You're welcome to do either. You must use graph paper and a ruler. That's because we need to be very specific and precise here. We need to make sure we can see exactly where those lines cross, because that's our solution. So first example, I'm going to try to color code here, and lucky us, they were given in slope-intercept form. So my first line I'm doing in green has an intercept at -2, and the slope is +1. So I'll go up 1 over 1 to do my graphing and connect that line. Try to be very careful. Use rulers in class. All right, next one I'm going to use red. +7 is my intercept, and this time the slope is -2. So I will go down 2 over 1, down 2 over 1, over and over again. And the solution happens where the lines cross, so I think that's right there. The coordinate at that point is 3, 1. That's the x and the y value that make both of my equations true. And if you ever want to check your answers, it's not a bad idea to plug that x and that y in, and it should make both equations true. I think that was it. Okay, next page. I've got my second example. And these are given in standard form, so I want to show you how to turn them to slope-intercept form if you like doing it that way, and then also how to do the intercept. So I'm going to turn the first equation to slope-intercept form. I have 2x plus 4y equals 12. If I want to turn that to slope-intercept form, I will subtract 2x. I'm left with 4y equals -2x plus 12. Notice I'm putting the x portion first and the number second. And then from there we would divide by 4. Make sure you do it everywhere. That's a very common mistake. Slope would be -1/2, and then my intercept would end up being +3. So there's my intercept. Use the slope, down 1 over 2, down 1 over 2, etc. And connect those dots. Okay, that was turning it to slope-intercept form. Some of you would probably rather find the intercepts. So for the second line, I'm going to do it that way. Remember, to find the x-intercept, you put a 0 in for the opposite letter. So we would replace the y value with 0. I'd end up with x plus 0 equals 2. Therefore, the x-intercept happens at 2, 0. That's right there. Then I'll do the same thing to find the y-intercept, only we're going to put a 0 in for the opposite letter. This time it's going in for x. So 0 plus y equals 2. Y-intercept is also going to be at 2. So 2 and 2. Now, that may not be enough for you guys to make an exactly perfect line, so you might want to find out what that slope is. Okay, to get from dot to dot here, what I'd have to do is go down 2 and over 2. That's a slope of -1, so that might help you make some more points. Or use that handy-dandy ruler. Okay, there are my two lines. There's the cross, and that happens at -2, +4 for our solution. And remember, you can always plug those x and y values in to double check. So, excuse me. All right, there are some special situations. I picked all lines that crossed, and they crossed once, and nothing crazy was happening, but that is not true for all lines. So I've got a little graphic organizer here to help you categorize your lines. You're going to have some questions in your assignment that they ask you to categorize these cases without necessarily graphing them. So you have two choices. Systems are either consistent or inconsistent. When they are consistent, they have a solution. Okay, they might have one or more solutions. When they are inconsistent, it means that they have no solution. So if you think about that, lines that don't cross would look like what? They'd have to be side by side. And they'd have to be parallel. That's what would have them have no solution. They would never ever cross. So what you're looking for, parallel lines have the same slope, but they would have to have different intercepts. So maybe write yourself a note on there. Same slope, but they must have different y-intercepts. So that's one way we're going to categorize systems. No solution, they are inconsistent. Within consistent systems, we have two options. Systems can be independent or they could be dependent. Independent systems are ones that have one solution. Those are the examples that we've just gone through. They have different m's, they have different b's. Both of the examples that I just did were independent systems. They cross once. Okay. The other option is to have infinitely many. So if you think about how it would be possible for lines to touch infinitely many times, if you had your first line look like this, and your second line looks like this, they would touch infinitely many times because they're the same exact line. So maybe put a note on there that they're exactly the same line. You're looking for the same M and the same B. Okay, so just to summarize here, our options are inconsistent. That happens when they're parallel, no solution. Independent, those are regular old systems, one solution. And dependent systems happen when they are exactly the same line and they have infinitely many solutions. So here are some examples. First one, my first equation in the first example is slope-intercept form. I want to turn the second one to slope-intercept form, so to do that, I'm going to subtract 2x on both sides. I'll get y equals negative 2x plus 3. This line and this line are exactly the same. So if you look back to our categories here, to be exactly the same, it's going to be a dependent system. Okay, and that means that they're exactly the same. They have infinitely many solutions. You don't necessarily need to include that in your answer, but it helps to know what dependent means. And then in the next one, this time they're given both in slope-intercept form. I noticed that these things have exactly the same slope. So they could be parallel or they could be exactly the same. So I bump over and I check their b's. They have different intercepts. That means that they're parallel. So think back to that little graphic organizer that we made. These are actually going downhill because they're negative slopes. But those are inconsistent systems. And that's because they have no solution. They don't cross. Okay, that'll do it. Remember, your book talks a little bit about tables, but we're actually not going to cover that. We're just going to do graphing, and then in the next few days we'll talk about substitution and elimination. We'll see you in class.